Welcome back to Calculus Conundrums. This is over limits, continuing limits, and feel free to subscribe if you like what you see. I'm going to just start out here, just going to show you what can happen when you have limits when x approaches infinity. So let me just show you here. You see this graph right here? Notice for this graph, notice that as x approaches infinity, in other words, as x gets larger and larger, notice that this graph tends to level off at this dotted line right here. And that line actually is, I probably should have labeled it, that's the line y equals 3. So that's y equals 3. So this would actually be what we call, this is what we would call a horizontal asymptote. Now over here, this line, let me label it a different way. So this line here is just the x-axis, y equals 0. So notice for this graph, notice as x goes to negative infinity, notice how the graph gets closer and closer and closer to this line, y equals 0. So these are examples of horizontal asymptotes. Now, a graph can increase without bound as x goes to infinity. So notice here on this graph, notice as x gets larger, notice as x gets larger, the y values get larger. So here, the limit of this graph as x goes to infinity would be infinity. And then notice this graph, as x gets larger, notice the y values get smaller and smaller. So on this graph, the limit of this graph as x goes to infinity would be negative infinity. So you wouldn't have horizontal asymptotes on these, but on the first two, you did have horizontal asymptotes. Okay, so what is a horizontal asymptote? Well, the line y equal L is a horizontal asymptote of the graph of f if the limit of f of x as x approaches infinity is L, or the limit of f of x as x approaches negative infinity is L. So actually, the L here is 3, because on this one, the limit of the function as x approaches infinity was 3, so that's the L here. And this one, the limit as x approached negative infinity was 0, so the L here was 0. Okay, so that's what a horizontal asymptote is by the definition. Now, one thing to remember about limits at infinity is, let's say r is a positive rational number and c is any real number. Then the limit as x approaches infinity of c over x to the r, where x is a variable and c is just some number, will always equal 0 as x goes to infinity. So if you took the limit of 10 over x to the 5th as x goes to infinity, that would be 0. If you took the limit of negative 2 over x to the 3/4 as x goes to infinity, you would get 0. So these exponents just need to be any positive rational number. Okay? Now, for when x goes to negative infinity, you have to make sure that x to the power is defined, but as long as it's defined, then this limit would also be 0. So the limit of 10 over x to the 2/3 as x goes to negative infinity would be 0. Now see, x can be negative numbers here because when you raise something to 2/3 power, you're taking the cube root of it, and since you can take the cube root of negative numbers, it's okay to say that this limit as x approaches negative infinity is 0. But if I tried to take the limit as x approaches negative infinity of 10 over x to the 3/2, well, this 2 right here means we have to take the square root. And since the square root of negative numbers is not real, you would not be able to evaluate this function at negative numbers. So this wouldn't make sense to say that x goes to negative infinity, since negative numbers aren't in the domain of x to the 3/2. So in that case, we would just say that limit does not exist. So now let me give you some guidelines for finding limits as x approaches plus or minus infinity. And these are with rational functions. So we're dealing with rational functions here. Now, don't worry about where these come from. These three properties here can be proven, but I'm not proving properties in these videos. I'm just showing you how to solve problems. So let's look at number one. Number one says if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. So let's take a look at this first example. Here the degree of the numerator is 3 and the degree of the denominator is 5. So based on number one, the limit of this function as x goes to infinity or negative infinity, either one, would be 0. Okay, so the limit would be 0. And it says see graph. Let me show you the graph. Okay, so I want to show you the graph of this function. So let me show it to you. This is the graph of this function. Now notice here, as x goes to positive infinity, see that the y values get closer and closer to 0. So basically this limit would be 0 as x goes to infinity. It would also be 0 as x goes to negative infinity as well. So you can see it goes to 0 there. And it turns out that this line y equals 0 is actually your horizontal asymptote for that function. Alright, let's look at case 2. Case 2. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the lead coefficients. Now when we say lead coefficient, it doesn't necessarily mean the first coefficient. It means the coefficient of the term with the highest degree. So be careful there. Alright, so here the limit of 12x cubed minus x over 3x cubed plus x squared, notice that this limit here, notice that the degree of the numerator is 3 and the degree of the denominator is 3. So therefore the degree of the numerator is equal to the degree of the denominator. Then the limit of this, whether it goes to infinity or negative infinity, would be the ratio of the lead coefficients. So that would be 12 divided by 3, which is 4. Alright, now let me show you that one. I got to turn this one off and I'll turn this one on. Now you can't really tell unless I actually type in the line, whoops, wrong one. If I type in the line y equals 4. Okay, now you can see that that red line is the line y equals 4. So you can see that as x goes to infinity, the graph is approaching that line, and also as x goes to negative infinity, the graph is approaching that line y equals 4. So in this case, y equals 4 would be a horizontal asymptote. Now the third case says if the degree of the numerator is greater than the degree of the denominator, then the limit of the function does not exist. So in that case, the limit would either be minus infinity or plus infinity. So in this example, it says, what's the limit of this function as x goes to infinity? Well, since the degree of the numerator is greater than the degree of the denominator, I would say that this limit does not exist. Now, if you want to know whether it goes to infinity or negative infinity, there is a way to figure it out. You saw me do this in an earlier video. Just pick a very large number, like maybe 1,000 or 10,000, and plug it into this. And if you get a positive number, you know it's going to go to plus infinity, and if you get a negative number, it's going to go to negative infinity. That almost always works. Obviously, there could be a place where it doesn't, but I'd say 99% of the time that would work. So now the other thing that would work would be if you cheated and looked at the graph, which is what I'm going to do now. So let me turn that one off, and let's turn this one on, just to get that one out of the way. All right, now look at this. See, notice that as x gets large, the y value just continues to get larger. So as x goes to infinity, the y value goes to infinity. So therefore, the limit of this function as x goes to infinity does not exist because it goes to infinity. And also, if you took the limit as x went to negative infinity, you can see that the y value would go to negative infinity. All right. Okay, so that's how you apply those three little rules to rational functions. There's three more examples down here, so go ahead. You can just pause the video here and look at each of these and apply the three rules up here to them. I do want to mention here, see, this is what I was talking about here. Somebody might see this and say, oh, the degree of the numerator is equal to the degree of the denominator, so we would do the ratio of the lead coefficient, and they might say, oh, well, the ratio, this is 1, and the coefficient, this is 1, and so they would get it wrong because they would think the limit is 1 over 1. But actually, when we say lead coefficient, we mean the coefficient of the highest degree terms, which would be -5 and +3. Okay, so that's the only reason I said that was a tricky one, is I didn't write it in descending order, so that could trick some people. All right, now I want to end this with one last statement. Many functions will have the same horizontal asymptote as x approaches infinity or negative infinity. So if you go back and look at a couple, the first couple we looked at, as x approached infinity or negative infinity, they both went to the same number. The limit went to the same number. But here's a function that would not have the same asymptote. And I'm going to show you this. It's a little tricky. And probably don't even need to worry about this unless you're a calculus student. If you're a business calculus student, I'd just skip it. I'd just skip this. Okay, so let's talk about what happens when x goes to infinity. Okay, when x goes to infinity, then we know x is greater than 0. So if we divide the top and bottom by x, so I'm going to divide the top by x and the bottom by x. So I'm going to divide the top by x, but when I divide the bottom by x, I need to use a square root so I can get, this inside the radical. So I would divide by square root of x squared, which is the same as x, and then I can put it inside the radical, and then simplify the top. 5x divided by x is 5, minus 1 divided by x is minus 1 over x. And then down here, 3x squared divided by x squared is 3, and then 1 divided by x squared is 1 over x squared. Now, when you take the limit of these four terms, this one, this one, this one, and this one, the 1 over x and the 1 over x squared is going to go to 0. So you'll just get 5 over square root of 3. So you'll get 5 over square root of 3, and then you can also write that as 5 square root of 3 over 3 if you rationalize it. So that is a horizontal asymptote. So as x goes to positive infinity here, you'll see that this horizontal line right here is the line y equal 5 square root of 3 over 3. Now, but if you let x go to negative infinity, you actually, when you divide by, since x is a negative number, see, x would be a negative number. If you just used x equals square root of x squared, that wouldn't make sense because that would only be a positive number. So to get it in the square root, we're going to have to let x be minus the square root of x squared so that it'll be a negative number. So then when we divide that, we go ahead and put the square root of x squared in here like we did before, but we leave the minus out here. Now all that's going to do is that's just going to change your sign. So all the other steps are the same, except you got that negative. You got that negative right there. And so when you take the limit, you're actually going to get 5 over minus the square root of 3, which is minus 5 square root of 3 over 3. So then you can see that if you let x go to negative infinity, it's going to go to this horizontal line. Okay, so you have two different horizontal asymptotes, one going one direction and one going the other direction. I'm going to cover slant asymptotes in the next video, but I don't really have time to do this application on this video, so just freeze the video and look at it and just read it and then move on.